In the world of fluid mechanics, understanding how liquids behave under different conditions is crucial. One key player in this field is the bond number, or BO. Simply put, the bond number is a dimensionless number that helps us understand the relative importance of gravity and surface tension in a fluid system. It's like a tug-of-war between these two forces, with the bond number telling us who's winning. Imagine a water droplet hanging from a leaf. Is it going to fall or cling on? The bond number helps us predict this. A high bond number means gravity dominates, and the droplet is likely to fall. Conversely, a low bond number means surface tension is stronger, keeping the droplet attached. The bond number is particularly useful when dealing with small-scale fluid systems, where surface tension often plays a more significant role than gravity. Think of tiny insects walking on water or the movement of fluids in narrow channels. In these scenarios, the bond number provides valuable insights into the forces at play. To grasp the bond number, we need to understand the two forces it compares: gravity and surface tension. Gravity is the force that pulls everything towards the center of the Earth. It's what makes objects fall and gives us the sensation of weight. In fluids, gravity acts to pull the liquid downward, creating a flat surface. On the other hand, surface tension is like an invisible skin on the surface of a liquid. It arises from the cohesive forces between liquid molecules. These forces are stronger at the surface, creating a tension that resists deformation. Surface tension is what allows small insects to walk on water and causes water droplets to form spherical shapes. The interplay between gravity and surface tension determines the shape and behavior of fluids. When gravity is much stronger than surface tension, fluids tend to spread out and form flat surfaces. Think of a puddle of water on the ground. However, when surface tension dominates, fluids tend to minimize their surface area, forming droplets or clinging to surfaces. The bond number is calculated using a simple formula: BO equals RGL squared divided by sigma. Let's break down each component of this formula. BO represents the bond number, a dimensionless quantity. Rho is the density of the fluid, which represents its mass per unit volume. Denser fluids have a greater gravitational pull. G is the acceleration due to gravity, a constant value on Earth. L is the characteristic length scale of the system, which could be the diameter of a droplet, the width of a channel, or any other relevant dimension. Sigma is the surface tension of the fluid, representing the energy required to increase the surface area of the liquid. The formula essentially compares the gravitational force, represented by RGL squared, to the surface tension force, represented by sigma. A higher bond number indicates that gravitational forces are more significant, while a lower bond number suggests that surface tension plays a more dominant role. Section 4. Bond number in action. A water droplet's tail. Let's consider a real-world example to illustrate the bond number's significance. A water droplet resting on a flat surface. The bond number will tell us whether the droplet will spread out or remain as a bead. If the droplet is large, the bond number will be high, indicating that gravity is dominant. The droplet will flatten and spread out due to its own weight. Think of a raindrop splashing on the pavement. However, if the droplet is small, the bond number will be low, indicating that surface tension is more significant. The droplet will remain relatively spherical, resisting the pull of gravity. This is why dewdrops on a spiderweb or water droplets on a freshly waxed car form near-perfect spheres. Section 5. The significance of the bond number in microfluidics. The bond number becomes particularly crucial in the realm of microfluidics, which deals with the behavior of fluids in extremely small channels and devices. In these microscopic environments, surface tension often overpowers gravity, leading to unique fluid behaviors. For instance, in microfluidic devices used for biological research, the bond number helps determine the shape and movement of tiny droplets containing cells or reagents. By manipulating the bond number, researchers can control the mixing and separation of fluids in these devices, enabling precise experiments and analyses. Furthermore, the bond number plays a vital role in understanding capillary action, the ability of liquids to flow in narrow spaces against gravity. This phenomenon is crucial in many natural processes, such as the transport of water in plants and the wicking properties of fabrics. Section 6. Conclusion. The bond number's broad reach. The bond number, despite its seemingly simple formula, offers a powerful lens through which to understand the behavior of fluids in diverse contexts. From the formation of raindrops to the design of microfluidic devices, this dimensionless number helps us predict and control the interplay between gravity and surface tension. By understanding the Bond number, we gain insights into a wide range of phenomena, from the everyday to the cutting edge. Whether we are engineers designing new technologies or simply curious observers of the natural world, the Bond number provides a valuable framework for understanding the fascinating world of fluid mechanics.